We're looking at this balance between bearing load and bearing life in design. And experimental data has shown that the relationship between the log of life, which is in cycles or revolutions for bearings, and the log of the force applied to those bearings is inverse and proportional to the logs. So this is intuitive. The higher the load you put on a bearing, the shorter the life is going to be. Of course, the lower the load, the longer the life. But lots of data collection has shown that relationship is constant and consistent for ball bearings and for roller bearings. For ball bearings, the rise over run is 3-to-1, and it's a little bit different for roller bearings. It's 10-to-3. So we can call that the slope. So it's -3 for ball bearings, and it's -10/3 for roller bearings. So the relationship that was developed is force times life to the 1/A equals some constant value, C, and that constant would be somewhere up here, the intercept, as we're going to see. So if I rearrange this equation, I get force equals C over L to the 1/A. If I take the log of both sides, I get the log of F equals -A log of L plus the log of C. And this should be familiar. In algebra, we call this a y equals m slope x plus b. And so that's the linear relationship on a log-log plot. And as we said, that slope is different for ball bearings and roller bearings. So A equals 3 for ball bearings and A equals 10/3 for roller bearings. Now this data collection is performed by manufacturers of bearings, and they usually report a value from their test data. So they do tests at high loads, tests at low loads, find that line, and then they report for the result of those manufacturers' tests, which is usually they're going to report the value of expected load for where 10% of the bearings fail for 10⁶ tests. So that rated force is often called C10. That's the rated force because that's being quoted as the catalog force where 10% are expected to fail. And that rated life, often called L10, is usually 10⁶. Not always for all vendors, but 10⁶ is the most common. So in my designs, I'm usually going to be interested in identifying what catalog bearing do I need to purchase. So I'm going to want to solve for the C10, and my force will usually be something different, something lower than the catalog force from the test data that the manufacturer is quoting. And so the way I compare it, let me take one step back. Remember we had this FL to the 1/A. So let's say that's the rated force times the rated life to the 1/A equals C. And because that's a constant, I know that for my purposes, my desired load times desired life, FD, LD to the 1/A is going to equal. So that's why I can ignore this C. So if I rearrange this equation and I use this principle that FR equals C10, then I can get C10 equals my desired force times the ratio of the desired life divided by the rated life to the 1/A. Now sometimes I have to convert that to hours. So to convert LR to hours, I will use the script L sub R, which is the life in hours, the rated life in hours. It actually doesn't matter if it's rated life, desired life. This is simply the conversion for life in cycles or revolutions to hours equals L in revolutions divided by N, so R, the number of revolutions per minute. We also call that RPM. We call that RPM usually. Times, we need a conversion factor, 60 minutes per hour. Revolution is going to cancel with revolutions. Minutes is going to cancel with minutes, and then hours goes to the top. This is in the bottom of the fraction, in the bottom of the fraction. So it goes to the top, so we get lifetime in hours. To go the opposite way, to convert life in hours back to life in cycles, life in, let's say, revs or cycles equals L script, which is in hours, times N sub R, which is RPMs, revolution per minute, times 60. Which is the conversion from minutes. Let's do an example. If the desired life of each bearing is 1 year of continuous operation at 1600 RPM for the shaft shown, what catalog load rating should I order for 90% reliability? Right now this 90% is key because the catalog ratings are typically already at 90% reliability. So I can use the catalog ratings directly. And what does my system look like? I have my shaft, bearing A, bearing B. I have a gear. There's a load of 400 pounds force, tangential on that gear, and there's a load of 300 pounds force directly down on that gear. And the distance from center of the bearing to center of the gear, 20 centimeters. The distance of center of the gear to center of bearing B is 30 centimeters. Let's start on the solution here. The resultant force on that shaft through the gear, force through the gear, is going to be the sum of the vectors. It's going to be 300 squared, the resultant vector, 400 squared. So that's going to be 500 pounds force. So that's going to be 500 pounds force on that gear as a result of the tangential load and the radial load. This is not thrust load. This is tangential load, just so you're not confused by the drawing. So if I balance those forces, I'm going to have a reaction force at A and a reaction force at B. I've got 500 pounds force here to here, 20 centimeters. Here to here is 30 centimeters. Take the sum of the moments equal to 0. So I go 20 centimeters over here. I have a 500 pounds force down. It's minus 500. I go 50 centimeters over, 50, and I get RB going up. So if I solve for RB, I get 10,000 over 50 equals 200 pounds force. 500 minus 200 is going to be 300. So I know that if I do sum of the forces equals 0, which is going to be RA going up minus 500 going down plus RB going up, which is 200, then I'm going to get RA equals 300 pounds force. I know my two forces on my two bearings. Now let's look back at the equation we're going to need to use here. We're going to look for the catalog value, the catalog rating for the desired force times the ratio of the desired life over the rated life in cycles to the 1 over A. In my problem, I didn't have rated life in cycles. I had rated life in 1 year of continuous operation. So I need to find that LD. It's 1 year of continuous operation. 1 year happens to be 8,760 hours per year, and then 60 minutes per hour. And then in my problem, it's 1600 RPMs. And this is going to tell me how many cycles or revolutions I need. 1600 revolutions per minute. So years cancel, hours cancel, minutes cancel. I end up with revolutions, and I get 8.41 times 10 to the 8th rev or cycle. And this is relevant. There's an application for things like cooling fans that need to run all the time. And so if they're running 1600 revolutions per minute, whatever the application is, for 1 year, that's 8.41 times 10 to the 8th revolutions. So then for bearing B, the C10 value is going to be 200 pounds force times 8.41 times 10 to the 8th over the catalog life rating. I apologize, I think I left that out of the problem statement. Let's put catalog life is 10 to the 6th, so 1,000,000 cycles is the catalog life. You can see here that this is 10 to the 8th, so at this RPM, 1600 revolutions per minute, you're getting far more than a 1,000,000 cycles, nearly 1 billion cycles. And additionally, problem statement should have said these are ball bearings, so our value here is 3 because it's a ball bearing. If we plug this into our calculator, we get a catalog rating of 1,888 pounds force. And when we look at that catalog rating, again, that's where only 10% of the bearings are expected to have failed, and 90% are expected to still be surviving for that amount of load with that amount of cycles. Then if we calculate for bearing A, C10 equals, the only difference here is 300 pounds force times 8.41 times 10 to the 8th over 10 to the 6th to the 1/3, and we get 2,832, 50% higher here, pounds force. That's great, but that's only an approach that works for only 90% reliability. So what if I want better reliability, like maybe 99%? That's what we will look at in the next video.